On behalf of 24houranswers.com, I welcome you to today's lesson. In this video, we're going to look at the long way of doing limits at infinity for rational functions. In a previous video, we did look at the shortcut for doing the same thing, and really I'm going to take this example right here, this function h of x, and I'm going to do it the long way to show you how we do get a limit of 2, and that ultimately leads to our horizontal asymptote at y equals 2 for this function. The same technique I'm going to show you now can be applied to all of these examples. I'm just going to show you one to motivate the idea in the event your instructor wants to see this technique on a test or a quiz or something like that. Just in case you didn't see it, I encourage you to go watch the video on the shortcut. This can be very helpful. It's very fast, but again, that is in another video. Please check that out. This example here, again, here's our h of x, and the long way of doing this, we're going to use these two ideas. If we find the limit as x gets really big or x gets really small of 1 divided by x to the n power, where n is a positive integer. So we're talking about 1 over x to the first, 1 over x squared, 1 over x cubed, any positive integer for n. If x gets really big and we take 1 and we divide by a really big number, we're going to approach 0. Check this out. 1 divided by, let's make up a number for x, such as 5, and let's square it. So 1 divided by 5 squared is 0.04. Well, let's let x get bigger. I'm letting x approach infinity. So instead of 1 divided by 5 squared, let's do 1 divided by 50 squared. Notice this number is going to be even smaller, and already I'm seeing the e negative 4. 4e negative 4 is really this right here, 0.0004. And if I press enter there, notice I get the same thing. I just want you to realize that this decimal, this answer here, as x gets bigger, this number here is going to get closer and closer and closer to 0. Let's do one more. 1 divided by, let's let x get a little bit bigger, such as 124 squared. We're going to get e negative 5 on this thing, so we're talking about this negative 5 moves the decimal over 5 places. The point I'm making here is this. As you let x get really big, or even if you let x get really small, sometimes this may be a negative number here, but that negative number is going to get really, really, really close to 0. Let's keep those two things in mind, and let's tackle this problem right here. So when you have a rational function with this technique, what you want to do is you want to look at the degree of your denominator. The degree of our denominator is 2. We want to divide every single piece in this rational expression by x squared. Again, we look at the degree of our bottom. We divide every single term by x squared. Had this been an x cubed, we would divide everything by x cubed. Had it been an x to the 50th, we would have divided all of these by x to the 50th. Let's do that right now. So there we go. As you can see, I took each term in my numerator, 4x squared, negative 5x, and 2, and we divided them all by x squares, and then we did the same thing to our two terms in the denominator. Again, it's all based off the degree of our denominator, x squared. That's how I got these pieces here. Now, let's take this rule up here, and let's apply the limit to each piece individually. But before we do that, let's simplify. This becomes 4x squared over x squared is just 4. We can subtract exponents here to get minus 5 over x. Notice we have one more x at the bottom than we do at the top. We cannot simplify that third piece up top, so it's 2 over x squared. Our denominator is 2 because the x squareds cancel out, and then we cannot simplify that last piece at the bottom. So let's apply our limit as x gets big. Well, that does not change that 4 one bit because 4 does not have a variable with it, so 4 is automatically going to be applied down here. If we let x get real big on this, this is where these rules come into play. Regardless of positive or negative infinity, a number over x to the first power, now here it says 1, but 5 is not going to change a daggone thing. It's still going to get close to 0 because really what we're thinking about here is 5 divided by a really big number. 5 divided by a really big number. If I do that, notice we're going to get something close to 0. E negative 9 means we move that decimal over 9 places and fill in a whole bunch of zeros. And the same thing is going to apply to this one. 2 over a really big number, that's going to be plus 0. So I'm applying the limit to each one of these pieces, and I'm using these rules up here. Then in our denominator, if we work all this out, well, the 2 is going to stay there because just like the 4, the limit of a constant is the constant regardless of where we're approaching. That's why the 4 and the 2 remain, but now notice we have plus 0 because if we plug a really big number into here and square it, 1 divided by a really big number is pretty much going to be 0. So working all of this out, we get 4 over 2, which is equal to 2. This is our limit as x approaches infinity. Well, it turns out the same thing is going to happen if we let x approach negative infinity. So if we go back now and look at the shortcut video or the highlights from the shortcut video, we did say the limit was 2. We saw the shortcuts there, and the shortcut here is this. If the degrees match up, you just use the ratio of the leading coefficients. 4 divided by 2 is 2. I encourage you to do the same thing with this one, and even this one down here. Just be careful with that 3. That 3 is what leads to our answer because the limit of a constant is a constant. And what you're going to realize here is that this right here is going to give you 0 if you apply that same technique that we did here. To motivate that idea, what you'd want to do for this example here is divide everything by x to the 4th because that's the degree of our bottom. What you would do with this one, you would divide everything by x squared because that's the degree of our bottom. And there you have it. One example of doing it the long way, focusing on the degree of your bottom. Take every single term in the numerator and the denominator of your rational function, divide it by that degree of your denominator, x squared in this case. Apply the new rules here. Don't ever forget these. These will be used a lot in Calculus 1 and Calculus 2. And then noticing that it simplifies down to give us a limit of 2. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.